Okay, so if you guys can hear me, so welcome to the session 3 of this course. So today in this live session, I'll be solving the questions for assignment 3. Alright, so I've shared the screen through one of the tablets and I'll solve on the screen, and as we go, I'll discuss how one should think about these questions and what are the correct things. So the first thing is, which of the following assumptions is incorrect for today's classical free electron model? Now, so this one is a very straightforward question, which says that the electrons in the metal are assumed to be free. Yes, that is a correct assumption of today's model. All the electrons in metal contribute to specific heat. Yes. The charge on electrons is ignored. This is the thing that is incorrect for Drude's model, because Drude's model accounts for the negative charge of electrons. Okay, and the electrons undergo collisions and between collisions they travel in a straight line. That's how mean free path is defined. And nuclear motions of atoms forming the metal are ignored, as they constitute a constant background among the sea of electrons. Now, as you go along, the second question is, the drift velocity of electrons is due to, now the word drift here means that in the presence of something the particles are drifted, and that something here that exerts force on the electrons is actually the external electric field. So when electric field is applied, electrons feel the force, and then they move along the electric field towards the lower potential. So these were two the very simple explanations for these two questions. Now, next one is, according to Drude's model, if the average conductivity, average, so there is a missing, there should be conductivity in a metal. If the average conductivity in a metal increases, I think this is the temperature. There's a misprint. Average temperature in a metal increases, the conductivity of, this is not temperature, this is tau, the collision time, in fact. So if the average collision time in a metal increases, the conductivity of the metal increases linearly or decreases. Now, as we know that conductivity varies linearly with tau, so as tau increases, conductivity also increases linearly. So
yeah, I think this question was not there in the quiz.
Is it?
Yeah.
There were okay,
three
since
three questions on this conductivity. So the first one was, according to Drude model, the conductivity of the metal. Then there were 4 options. The second question was, according to Drude model, the conductivity of the metal near room temperature.
Okay, so what I have and what I am supposed to do in this course is actually to solve the previous assignment questions, previous courses assignment questions, not the exact one, but coincidentally the previous year's questions are exactly similar to this one, but just shuffled one.
Yeah, but this was not there anyway. No issue.
Okay. We will see that if these questions turn around in some other numbers. So this conductivity increases linearly with the collision time between the two collisions. Now the other question says that, according to this Drude model, conductivity of metal near room temperature. Now as I have mentioned above, conductivity goes as Ne square tau by m, and the collision time tau decreases with the increase in temperature because of the increased kinetic energy of the electrons. They go zigzag motion more. With increase in temperature, tau decreases, and therefore conductivity also decreases linearly, because if temperature increases,
Excuse me,
yeah,
I have some issue with this question.
yeah,
Is according to Drude model, the conductivity of a metal near room temperature. Now,
yeah,
if you see the options, the option, let's say C or D,
yeah.
it is saying increases linearly with temperature. Now, it does not say whether increasing temperature or decreasing temperature. Similarly,
Now
T,
the thing is the statement increases linearly with temperature. This in general means increase in temperature. I mean, in a conventional reading sense, but yes, one should have mentioned clearly with increase or decrease.
yeah, similarly, the said next option decreases linearly with increasing temperature or decreasing temperature.
Exactly, you are right. But in a conventional sense, one would think and one would see in
Yeah, okay,
in terms
yeah,
of
it's,
increasing
I had
temperature.
difficulty to follow, so that's why I'm
Okay,
telling.
okay, okay.
Yeah,
So if temperature increases, tau decreases, and that would decrease the uh, electronic conductivity, and therefore the option would be the the conductivity decreases linearly with temperature as relaxation time decreases with temperature. Now this one is say that the at high temperatures the relation between conductivity and metal is, now at higher temperatures, as we have seen, and now near room temperature we have seen that conductivity decreases linearly, but at high temperatures conductivity goes as a hyperbolic sense. So in that scenario, uh, conductivity versus temperature curve would be is inversely proportional to T, because sigma into T would then turn to be constant, and as temperature increases conductivity decreases sharply. Okay. Now moving on, the electrical resistivity in the next question, electrical resistivity of copper is approximately 75% of that of electrical resistivity of gold, while the electron density of gold is approximately 70% of electron density of copper. Now if you just write down these two terms, as electrical resistivity of copper is 0.7 times electrical resistivity of gold, whereas the electron density, now if I write it that 0.7 times of copper is actually they have provided the electron density in case of gold, right? So this electrical resistivity is in fact the reverse of conductivity. Now one can modify the equation in terms of this thing, 0.75 remains on top, and sigma AU. One can modify this thing again by saying that sigma AU is 0.75 times sigma of copper. Now taking this ratio, sigma AU divided by sigma of copper, which is 0.75 now, and as we know that the conductivity is Ne square tau by m, one can write N of gold E square tau of gold divided by mass of electron complete divided by N of copper E square tau for copper divided by m. E square by m cancels, and if you shuffle these two sides away and put the value of n AU divided by NCU, which we have found out here is 0.70, this would turn out to be N for copper, tau for copper divided by tau for gold would be nothing but 0.70 divided by 0.75, which is 0.93. It's a pretty straightforward question, and the correct option would be the ratio of these two collision times would be 0.93. Now this moving on to the next question, that's the question number 7, that at room temperature the electrical resistivity of gold found to be 2.20. Let me just write it down. And the density and atomic weight of gold are given so and so. Now, as we know, sigma is n e square tau by m, which is given by 1 by rho, because conductivity and resistivity are inversely proportional to each other. So here one can rearrange this equation for tau, m divided by n e square rho. Now the important thing in these kind of questions is that one should maintain same convention of units. So if one takes mass to be in kilograms, then mass of electron is 10 to the minus 31 kg divided by the charge density. Now charge density we can calculate from the following information that is given to us, that weight of gold is density is given, that is 19.3 grams per centimeter cube, and n is the number, that is number of electrons present in 1 centimeter volume. So 197 grams of gold would count to Avogadro number, that is 6.22 times per 23 atoms, and we are given that each atom contributes 1 electron for the conductivity. Then we can replace atoms by, we have 197 grams of gold contains Avogadro number of electrons, and therefore 19.3 grams would contain 6.022 divided by 197, 19.3. This is the number n which we want, and then if we plug in these values here, we get 10 to the minus 31 divided by 6.022 into 19.3 into 10 raised to the power 23, 197. Charge on the electron is E square, which is nothing but 1.602 into 10 to the power minus 19 coulombs square, and multiply by the conductivity, the resistivity. Now resistivity given to us is 2.2 into 10 to the minus 6 ohm centimeter. Now important thing to note is into 10 to the minus 6 ohm centimeter. Now since we are using SI system, we should also convert centimeter into meters. That would count to be 10 to the minus 8 ohm meter. So if again plugging this value at the denominator and solving the algebra, one would get the tau to be 2.7 into 10 to the minus 14 seconds.
Yeah, excuse me.
Yeah.
So this density is coming in terms of centimeter cube, right? The density of electrons, n.
Oh, sure. So okay, this is in per centimeter cube. Thanks. That would count to be a factor of multiplicative factor of to be 10 to the power 6, that is per meter cube. Yeah, I forgot.
Yeah, actually, I did this calculation, but I could not get this factor 10 power minus 14.
Okay.
I checked many times. I don't know where I did mistake.
Okay.
Can you explicitly calculate if is it possible?
Okay. I'll do this calculation right away on the screen.
Yeah.
So as we know, m divided by n e square rho, and we have 9.1 into 10 to the power minus 31. I'll just use a big denominator here, and we have found out to be 6.022 into 10 to the power 23 multiplied by 19.3 divided by 197. This is n, and e square 1.602 into 10 to the power minus 19 square, and rho we have and just to multiply here, we have a factor of 10 to the power 6 coming in due to n, which I just missed again here. 10 to the power 6 factor, and resistivity would be again in denominator. I should write 2.2 into 10 to the power minus 8 because this is here. Okay, so let's do the explicitly and collect the numeric numbers on one side and 10 to the powers on other. 9.1 divided by, now if you solve this particular portion, you would find it to be 5.89 into 10 to the power 22, in fact 0.589, I should write it as 0.5, yeah, 0.589 into 10 to the power 23, and we have 10 to the power 6 here. Again in denominator we have 10 to the power minus 8. This value would count to be 10 to the minus 38. 1.6 square would be 2.56. We also have 2.2 here in the denominator. I think we are all set. So 10 to the power 23 and 10 to the power 6 would be 10 to the power 29. This would count to be 10 to the power minus 46, and this 10 to the power minus 29 would add up to 10 to the power minus 31 to be 10 to the minus 60 in the numerator, and 10 to the minus 46 would go in the denominator, would be 10 to the power plus 46, which I am removing to write 10 to the power minus 14 in the numerator. And the terms which we are left in the denominator are 9.1. I'll use a separate color, this term and these two terms. That's all other terms are 10 to the power, which we have already taken care of. So 0.589 multiplied by 2.56 multiplied by 2.2. So if you do this thing via calculator, I believe one should get the correct result. Let me do just 9.1 divided by 0.589. These two terms counts to 15.44 divided by 2.56 multiplied by 2.2. This counts to 5.632 multiplied by 10 to the power minus 14, and if one does an exact calculation, 0.632, it is 2.7 into 10 to the power minus 14 seconds. So it is coming 2.7.
Yeah, thank you.
Okay.
Yeah.
So the correct option would be 2.7 into 10 to the power minus 14 seconds. Then moving to next question. The classical free electron theory Lorentz number, now since this is straightforward question, the Lorentz number is given by 3 by 2 kb by e square by Weidemann-Franz law. Okay. Then we have, now this question is more or less a straightforward postulate that and a result that comes from Drude theory, that the classical free electron theory failed to explain the electronic specific heat Cv of metals because experimental value of Cv is, now as we know that experimental value of Cv is 10 to the minus 2 times of Cv Drude model. So it's 10 to the power minus 2 times smaller than the calculated value, right? And Then we have question number 10. How does Seebeck coefficient calculated using Drude model roughly compare? Now this is again argument that the Seebeck coefficient determined exponentially is again 10 to the minus 2 times s calculated by Drude model is actually again is of calculated is 10 to the power 2 times greater. It would be opposite, so calculated Seebeck coefficient would be 100 times larger than the experimental value. Now moving on to question number 11, the Fermi energy. Let me just find out where I have solved this thing particularly. Okay, now Fermi energy for copper is given by EF equal to 7 eV equal to 7 eV. Now we know Fermi energy is given by h cross wave Fermi wave vector square divided by twice of mass of electron. And what is the Fermi velocity? Now Fermi velocity, first to calculate Fermi velocity, what we can do, we can relate this thing to the kinetic energy of the electrons in copper as half m Vf square. Okay, so what this gives us, this is the Fermi velocity, and we can directly plug in these values to here. We can calculate Vf to be 7 into 2 divided by m square root. But just one thing to note here is this is in eV because we have 7 electron volts and eV is inside the square root. So now if I change these numbers to SI units, it would count to 14 multiplied by charge on an electron is 1.602 into 10 to the power minus 19 coulombs divided by mass of electron in kilograms to be 9.1 into 10 to the minus 31. So 10 to the minus 31 goes up and gives me a factor of 10 to the power 12, which after square rooting comes outside comes to be 10 to the power 6, and answer would be in meters per second. Now if one evaluates this factor with the square root, it roughly comes out to be 1.56 into 10 to the power 6 meters per second. So the Fermi velocity would be option number A, 1.57 into 10 to the power 6 meters per second. So is there any question in these things till now?
No, this is fine.
Okay. Now moving on to the next question, that is question number 12. Let me find it out. Yes. So in this question, the density of silver is given to be 10.5 grams per centimeter cube and contributes a single electron per atom, as we have seen earlier where it was gold or copper. Now the question is, what is the plasma frequency of silver? Now plasma frequency omega p square is given by 4n pi e square by m. Now if one plugs in all these values here by calculating the electron density from the value, the information that we have given to us, 10.5, and so it won't be I've seen that this will not help here. So instead of this, what we would do, and just I can do this thing, but I found this alternative expression for omega p while searching some in other books is n e square divided by epsilon naught m. So this is mostly a conversion of system of units where the term 4 pi in the numerator is replaced by the term 1 by epsilon naught in the denominator. plugs in these values, n as compared to this as compared to the previous question can be found in the same way as 108 grams of silver gives you Avogadro number of atoms. So how much 10.5 would give us? So, that n turns out to be 5.85 into 10 to the power 28. Now we have accounted for the meter cube as well. This value is n, and if one does a squaring of electric charge, 1.602 squared into 10 to the power minus 38 divided by epsilon naught, value is 8.85 into 10 to the power minus 12, and mass of electron in kilograms is this. Now if gradually, as if one solved this question, one would find such prefactors: 80 by 535 multiplied by 10 to the power 33 whole square root, and after simplifying, this turns out to be 1 by 2, giving 3 tens here, or 110. So 1.859 square root into 10 to the power 16. It turns to 1.363 into 10 to the power 16 hertz. So this one can easily find out, and the correct option would be a positive 1.35, very close to the solved answer. 1.35 into 10 to the power 16. This would be the plasma frequency for silver. And now moving on to question 13th. Now this is an argumentative question again, that if the plasma frequency of a metal is omega p, for which frequencies of light the metal will be opaque. So what we have seen that dielectric constant in these systems is given by just find out. E of omega is 1 minus omega p square by omega square. So when omega, the incident light, is greater than or is in fact less than omega p, then E becomes negative, because if omega is less than omega p square by omega square becomes greater than 1, and therefore E omega is negative. Now for such negative dielectric thing, now if you plug these negative dielectric in the dielectric constant value in the wave equation that is used for propagation of a wave inside a material, one would see exponentially decaying solution. Exponentially decaying solutions for the restriction that when dielectric constant is negative. And exponential decaying solution inside a material means that the wave is not going to penetrate it, and therefore the material or the metal will be opaque. Now this condition is only satisfied when omega is less than omega p, and when omega becomes greater than omega p, the material becomes semi transparent or behaves as glass. So these are the two things. Now moving on to the next one, which says that what is the threshold wavelength for lithium below which it becomes transparent. Now using this again the same analogy, the threshold wavelength, now we know that wavelength and frequencies are inversely related to each other. Now if we are to find the threshold wavelength, we are again to find the threshold frequency for which it becomes transparent, and the value given to us is n is equal to 4.7 into 10 to the power 22 per centimeter cube. So again using the relation omega p as square root of NE square by epsilon naught m. Now this omega p,
Excuse me.
yeah,
I have a question here. That omega p is in the, is it the circular frequency or linear frequency?
this is the angular frequency.
So that will come in radian per
Yeah, yeah.
second.
So one has to
So you
do,
have to 2 pi. You
yeah,
have to.
yeah. One has to write 2 pi.
So previous question also we have to multiply by 2 pi. The
Oh,
previous, I mean, in order to find the linear frequency f, we have to divide omega by 2 pi
okay.
because it is coming in hertz.
Yeah.
So you have to multiply by 2 pi, no? I mean, divide by 2 pi, no? Because omega is coming in radian per second.
Uh-huh. Okay. Okay. I understand. So division by 2 pi would lead to 2366 factor, and okay, you are right, here. Omega p would be 2 pi nu. But I think that the plasma frequency is mostly related to the angular frequency part, right? But if one is to suppose to calculate the wavelength of that particular light, then the 2 pi part comes in.
Radian is anyway dimensionless, so we
Yeah,
can just say simply by per second. But I still have little bit. Because it is in the question, it is saying that find out the frequency in terms of hertz, something like that. It
yeah,
is written.
per second is hertz.
So that's why I had a confusion. Should I divide with 2 pi or not?
Okay, but I think the reference. I mean, you are right here again. The reference of plasma frequency, which I believe that goes clearly with omega p, and as I will mention here that if one is to find out the threshold wavelength, then this wavelength cannot be found out until unless you bring in this factor of 2 pi here.
So there is a little bit ambiguity here.
Yeah, yeah.
Okay, fine. Yeah.
So if you change the frequency to be speed of light by lambda and solve this part, n given to us is 4.7 into 10 power 22, which is in centimeter cube, and converting into meter cube, it gives a factor of 6 to it. Then we have e square is 1.602 square, that is 2.56, and then 10 power minus 38 divided by, I have epsilon naught into 10 power minus 12 into 9.1 into 10 power minus 31. The whole half is given by 3.3 into 10 raised to the power 8 divided by lambda multiplied by 2 pi. So if you solve this thing further, you would find such situation: 6 pi into 10 power minus 8 divided by 1.22, which comes around to be 15.45 into 10 power minus 8, and giving 2 tens 2.4, one we can say 1545 into 10 power minus 10, which is nothing but the angstrom, and the very close approximation to our solution is 1560 angstroms. Okay, then we have our next question. Now this is based on Hall effect. If I write the Hall voltage, that depends upon the current going into the sample, and the magnetic field, magnitude of the magnetic field divided by the concentration of the charge carriers in the charge on an electron divided by the thickness of the material. Now if And using this following relation, we can easily say that Hall voltage increases if the number of charge carriers goes down, current goes up, and magnetic field goes up. So electric current decreases, no. Magnetic field, no. And the correct option would be number of charge carriers decreases, we'll get more Hall voltage. And the next question is again can be done by a simple diagram, that if both the direction of current and applied magnetic field is reversed in a Hall effect experiment, then we have, now this can be found out from the Fleming's left hand rule, that suppose we have a situation like this and magnetic field is going in this direction, we have applied the current in this direction, and using Fleming's left hand rule we'll find that electrons will feel accumulation on this because the force will act in this direction. And if we reverse the direction of magnetic field down and the direction of current in this way, so Fleming, you work out with Fleming's left hand rule, it will again say that the force will be acting on the direction in the same manner. So the magnitude and direction remains unchanged. And all other options give us some reduction or some reversal of directions, which is not happening in the present case. Now moving on to the next question, we have our metal cube of dimension 2 mm by 2 mm. Let me just find out, this is here. Contains 2.4 into 10 power 19 electrons. The magnitude of the Fermi vector of the system in the quantum free electron approximation is, now volume given to us is 8 mm cube, which is nothing to say, 8 into 10 to the minus 3 centimeter cube, and n we have is 2.4 into 10 to the power 19 electrons. The Fermi wave vector is given by the relation 3n pi square raised to the power 1 by 3. Now if you plug all these values inside, if I bring 3 pi square raised to 1 by 3 multiplied by n, which is nothing but the number of electrons per unit volume, 8 into 10 to the power minus 3 raised to 1 by 3. So this counts to 24. One point we can take here, 10 to the power 18, and 18 and 3 becomes 21, and 24 by 8 is 3, nothing, is 1 by 3. And if you work out, it counts to be 3 pi raised to the power 2 by 3 multiplied by 10 raised to the power 7. Now all the options are in centimeters, so we kept the volume also in centimeter. Gives to be per centimeter, and the correct option would be 3 pi raised to the power 2 by 3, which is option C. Alright, then we have question 18, which says if the number density of electrons in 3 dimensions is increased 8 times, if n is increased 8 times. Now since we know that kf is 3n pi square 1 by cube, so if n goes by 8 times, 8 cube root comes out to be 2, so kf increases only twice. And since kf is related to the Fermi energy as h cross square kf square by 2m, now kf squared would increase the Fermi energy by 4 times, and Fermi energy can be equated to the temperature kBT or 3 by 2 kBT. So temperature, so since 3 by 2 is a constant, so we can say Fermi energy increases 4 times, so temperature must have gone up to 4 times. So Fermi temperature, in fact I should write TF here, will increase by a factor of 4, right? Now this is 19th question we have, saying the density of silver is 10.5, assuming again 1 free electron per atom. What is the Fermi energy of the silver? So we are given with n, we can find out n in the same way. Since this is 10.5 and we have 108, if we work out, n comes out to be 5.85 into 10 to the power 28, a number that is per meter cube. We have converted into, because we have done it once or twice in between of the solution. Now this number comes out because let me just do it explicitly again, if not we are not running out of time here. So 108 grams comes out to be a Avogadro number, then 10.5 would give us 23 divided by 108 into 10.5, and per meter cube would be 10 to the power 6. If you evaluate this number, this is nothing but 5.85 into 10 to the power, and 5.85, and it will be 0.85 in fact, 0. 10 to the power 29, 5.85 into 10 to the power 28 per meter cube. This is the value of n we have. And to calculate the Fermi energy of silver, we have this relation with us, Kf square. Now further, Kf is related to number density as by the following relation. Okay, so let us plug in these values inside and find out. Now to h cross is nothing but h by 2 pi, so I'll write it in this form. We have 2m. Kf square would give me 3n pi square raised to the power 2 by 3. So this is nothing but h square by 4 pi square into 2m. I can take out 3 raised to the power 2 by 3 outside, then pi raised to the power 4 by 3 outside, and the number density remains as n 2 by 3. So h square, h Planck's constant in SI terms to be 6.626 into 10 to the power minus 34 squared divided by 4 into 8. Mass of electron gives me 9.1 into 10 to the power minus 31, and this pi square and this 4 by 3, if you work out, it gives me pi raised to the power minus 2 by 3, which I can write as this 3n by pi the whole raised to the power 2 by 3. So I'll solve this part first. 3 multiplied by 5.85 multiplied by 10 to the power 28 divided by 3.14 raised to the power 2 by 3. Okay, this gives me 5.589, because 3 and 3.14 are almost equal, and since it is just greater than 1, the numerator will be just less than the initial value, into 10 to the power 28 raised to the power 2 by 3. We can take one value from 28, 55.89 into 10 to the power 27, so that it becomes 10 to the power 9. We can cancel out by 3 into 9 is 27. So what I can do here is again goes is 2 by 3. Now the initial part, if one evaluates, it comes around to be 0.603 into 10 to the power minus 37. So multiply these two parts and we are done here. And I can write 6.03 into 10 to the power minus 38 multiplied by that. Now this comes around to be 14.61. This part 618 into 10 to the power 18, because 3 would become 9 and 9 into 2 gives 18, and 55.89 it is for 2 by 3 would give me 14.618. 6.03 10 to the power minus 38 is nothing but 88.146 into 10 to the power minus 20. So this value is in joules. We have the Fermi energy which we were calculating. Now to turn into electron volts, I can divide it by 10 to the power minus 19, and if I solve it out, if I do 10 to the minus 20 here, then it becomes 16. 16 and 88 are connected by 5.44 approximately eV. So our option, very close call, would be 5.5 eV. Right. So is there anything that one wants to ask?
I think for me it's fine. No other question. Another just one clarification: in the final exam, the calculator will be allowed.
I hope it should be, because
Yeah. No,
yeah.
that's why I'm asking, because some exams they don't allow calculator.
Okay, I think it should be, because unless it will be very difficult to calculate the cube roots and 2 by 3 powers on hand.
Yeah. Okay.
Right.
Okay. From my side, fine. No problem. Thank you.
Okay, thank you. And there's one more participant, Mrs. Sujata Roy. If you have any questions, you can ask. Or
No, it's okay.
okay. Okay, then since there are only 2 participants in the present session, if we don't have any question, we can stop the presentation here, and I'll meet you in the solution of the next week session, next assignment next week.
Okay.
Thank you.
Okay, thank you. Thanks a lot for joining.